So first, let's download the data. It's called audio NIST. You're probably familiar with NIST for written digit recognition. We can click download, and if you do it first time, probably it will ask to enter with your credentials or with Google account. So let's first download the data, and let's open Colab, create new notebook, and upload here this data. Downloads. Okay. And first that we will do, we will unzip it. So we can just type exclamation sign, and I will enlarge the font. How can I do that? I'm sorry, somebody knows how can I enlarge the layout in Windows? Control plus, so it's like in, oh cool, thank you, John. It's like in Apple. So we have our data, and this one, unzip, and the name of this file. And we will have here the folder with the recordings, and in this folder, it's pretty big, so it takes time to open. You see the digits pronounced by George, by Jackson, and so on. A lot of digits. In Python, there is a useful function to work with the folders called pathlib. So we will import the library pathlib, path library, and let's create the variable with our path to data. Which is spoken digits. I'm not sure if it will allow. Oh, okay, it allows to use the shortcut. And recordings folder. So in your homework 5, you will do the same procedure. Yeah.
You might just going back up the unzip. I think I missed this.
Oh yes, sorry, I was fast. And just for reference, I also want to let you know that you remember there was the first presentation on Python, you can go there. Last year we did more tutorials on Python, so you can go there and find tutorial number 3, which is almost the same as today. So you can see also here the syntaxes, just for reference in the future. So just exclamation sign, unzip, and the name of the file. So in your homework, you will need to start also with downloading data. You will have a lot of songs, also separate accompaniment and separate voice recordings. It will take around 2 hours to download. And then you will create the data set. So it's pretty similar to what we are doing today. So let's create the list of all the files in this folder. So I will show you how we can do that. So just a random variable, we didn't use it later, so I don't care about the variable. This pathly dot path, and we indicate the path to our data. And now we can use method rglobe. It will go through all the folders, also enclosed folders, and create a list of all files with a specific what is called the specific .wav. What's the name for the engine of files? Extension, probably. Okay, so let's do that. Dot rglobe, and we indicate all the files that finishes with .wav, this regular expression, and we can try to take a look at our data, and you can see that it says it's not a variable, but it's generator. Generator means that we should access to it in for loop, like for a variable A2. In this generator, we can, for example, print A2, and I want to break it. So let's write, for example, I equals 0. Or wait a second, and we can break immediately. So you see, we can iterate over the generator, and the elements of this generator will be the paths to our audio data. So if we want to create a list, from generator, we just can type list and our generator, and it will return our generator is one, the list of all the audio files. Okay, so this is the first step. We create the list of all audio files in specific folder. Now we want to use these paths, for example, and this object in Torch is called Dataset. So let's create a dataset. We will import Torch. We will import Torch audio. And we import the dataset and DataLoader classes from Torch library. These are just useful functions that will help us to create a dataset. In DataLoader. So we will need for now these functions. And let's create our dataset. So we create a class. Let's call it Muniz. You can give any name. And it will be based on the dataset class that we imported. And so dataset class in PyTorch has only three functions. One function is called initial, when we initialize our object of this class. So we will initialize our class with the path to our folder. So path to data. Then another function is get item, when our class will return the item. So it can be only the path to audio file, it can be audio file, and it can be spectrogram that we will use actually. We will use spectrograms. So another function is get item. I don't know, probably there are not three but four functions, because I still get attribute, but I never seen okay, so let's see. So it will index. It will be the index in that list of all the paths to our audio files. And this last function is the length of our list, the number of all audio files in this folder. Len. So let's write this class. First, we create the list of all files in this path to data. So let's define, because it will be variable inside this class, we use self. Self will refer to this, the object of this class. And then we create the variable. So path to data, we will initialize this variable with our path to data input to this function. So when we will create the object of this class, it will automatically create this variable self path to data. Now we want to create the list of this path to data, and also we will create the object as we did it before, this pathlib.path. Pathlib.path. Now we'll create the list of these files. Dot paths, for example, or I could just probably write list in front. So we create list self data our globe and indicate all of our files. So we initialized our object with the list of all audio files in the given folder. Okay, then get item. We can, let's first write here. The length will be the length of this list. Return len of self dot paths. And get item, we can return, for example, audio, but for now, let's return only the path self paths. Index. Okay, let's try it now. Create the class dataset and path to data. So we can take and take a look to see its length. It should be like it has this len of the data set. And we see we have 3,000 audio files. And we can get an item, so we can use dataset dot get Oh, wait a second. We even don't need to type it because it's with two underscores. So we can just access with the index. Let's try to access. So if we are trying to access the path in our list, you see it returns not a string, but specific type of data. To get just a string, there is the method posX as posX. It will return the string. Just posX. So it will just return the full path to the file with number 2 in our list. Does it make sense? Does it make sense to you? So we created a class. The input is the folder, and now it creates the list of all audio files in this folder, and we can access to the path by index. Does it make sense? And yeah, if you want me to go back, just let me know if you want to see the synthesis. Now, for our training, we want not the path to the audio file, but the audio file itself or the spectrogram of this file. So let's modify our initialization function. So let's create the spectrogram. Wait a second, probably we can return the audio file just to play. We can return the audio file itself, for example. If we write torch audio load, then when then it will return the audio file, and we can play it. To play it, we need import on Python audio. And we can play it. We should specify the frequency. Okay. It's not SR, it's read. And what else?
That's right. The return of tuple. The return of tuple is the which audio lower.
Audio.
Probably only one.
Uh,
So dataset after dataset at one. Oh, sorry. 0.
because on squeeze.
Dataset for now. I think I can do it.
So or
I don't know.
oh, I see, because because torch audio load, yeah, it's my bad. Torch audio load returns file and sampling rate. So probably I could just use without sampling rate. Let's see if it works. Oh no, so yeah, probably the audio file and then sampling rate. Okay, we can hear, listen to it.
4.
So we can try another data in our data set.
4.
So it's another speaker. Okay, and finally, let's return not the audio file, but its spectrogram. Okay. Usually, because we want to classify, classification is much easier problem task than generation of audio. So we can use less features, not the spectrogram, but MEL spectrogram. If you know MEL spectrogram, just shrinks the high frequencies. So let's create the transformation from audio to MEL spectrogram. In your homework, you will need spectrogram, not MEL spectrogram. But this syntax is pretty the same. Spectrogram, and here we indicate the number of frequencies, sample rate, you can see where I'm typing. Oh, then the number of MELs, of frequencies in MEL scale. First we create to create MEL spectrogram. It first creates spectrogram and then converts into MEL spectrogram. So first we indicate the number of frequencies in ordinary spectrograms. Let's say 2 power 10. Window length. The same. And even not indicated hole size. And the number of mails. Usually people use 60, 80 mail. Okay, this is our, so this transform will be created with the creation of the class. So we will not create it every time when we read the file. So that's why I put it in the initialization part. We could also write it later, but it doesn't make sense. And here we read our file. And then we apply this transformation, return self-spectrograms to our item. Let's see what it will return. Set, for example, 1. So you see it returns this shape, so 80 frequency mails and 15 time frames. If we don't want the first dimension, we can unsqueeze it. On this, yeah, let's unsqueeze it for now. Squeeze it. And also, in your homework, you don't need to apply log scale to spectrogram. But because you can have a lot of zeros in the silence parts of the speech, we can threshold the data with some small numbers. So there is a function clump that, and here we indicate what we will write instead of numbers below, like negative power, the 10 power negative 5. Just because if in our data a lot of zeros, it will be, first of all, if we transform to log scale, log of 0 will be infinity to avoid this. And in the homework for training, it's also better to have less zeros in the data. That helps to have non-zero gradients. Okay, and now I will take, let's plot it. So to plot it, import matplotlib. Let's plot okay, it's upside down. We can indicate origin. low. And it's difficult to see, so let's apply log scale. I will take just natural log. For training, it doesn't matter that it's not base 10. So now it's brighter. Okay. The dataset now, the dataset class returns the spectrogram. Also, it should return the label of the data or label of this number, because how we will train our model? We will take the spectrogram, pass it through neural network, and the output will be array of 10 numbers, and we should compare with the target number. So let's also create the target output in our data set. Okay, so we return spectrogram, and also we should return how can we get the number we can use the path to our data, and you see that the first digit is the target, the label of our data. So we will take this digit from the string as the target. Okay. So we can write, it will return string, so we will take the integer of this. You remember that we created the list of these files, self paths. Let's take index. Index. Then yes. Then we will split it. By the slashes, and we will take the last part of this and the first digit. Let's see if it works. So let's see, data set. Now it returns the spectrogram. Yes, and the label. In your homework, your data set should return 2 spectrograms. One spectrogram of the mixture of audio, another spectrogram of the only of the vocal. And then you will try to eliminate frequencies from your mixture that matches on the 2 vocals. Okay. Yes. Well, yeah, because here we have digits from 0 to 9. If it has 2 numbers, then probably you can use here just 2 positions, and or probably you can split again. Split, because you remember there was digit and underscore. Probably you can split again by the underscore. Now we should create the batches because in in our because in the training process we should have several files in the just to make faster the training, and it's called a batch. To create a batch, we need another class which is called DataLoader. So Dataset just returns one object. DataLoader will randomly, if we indicate this option, choose files and return the batch of these files. So I think we don't have time to go through all of this, and let's do the next thing. I wrote this, so I will open my prepared presentation. 1 second, because otherwise we will not cover all this stuff. So on this step, actually, when you do homework, you can try to inverse, to create from spectrogram audio again. It's good because in the end of your training, you will still be asked to create audio. Okay, so how to create probably let's cheat. I will upload files here. And while it's uploading, I wanted to share with you the result of the homework 3 on bit tracking. Yang Wang, I pronounce correctly. Yeah, I just wanted to share with you your bit tracking results that I think sounds great. So let's don't you find that it's very precise? Okay, great job. So, what?
The catchy song.
Okay. Especially when you listen to it hundreds probably times. Okay. So to make this short, I will just use my prepared so the second step is to create data loader. Data loader, as I said, takes the specified number of files. You can say like 5 files or 8 files. It depends on your memory available. By the way, I trained the homework 5 on this laptop. This laptop has 1.5 gigabyte NVIDIA card, and it was enough for training. So probably you don't need to use BlueHive because it's not easy to understand. But if you have questions, just you can write me email and I can help you with BlueHive setting as well. So the DataLoader, where was it? The DataLoader is built-in class, so you just indicate the dataset or over which it will go through, and if you need, shuffle them, and the batch size. The problem with audio is that they have different lengths. So there is a special function for this. You can write a function that will add zeros or cut, for example, frames to make all the files of the same length. So in this case, I just added zeros. For your homework, I would just find the minimal number of frames and just took these files. And now, if we iterate over DataLoader, you see that every time it returns, in my case, 5 files. So it takes arbitrary 5 files, creates everyone for them. And so you see that in this batch, the maximum length was 16, and this batch maximum length was 17. And here is the tender with labels for these digits. And this is the first step. The second step is to write the model. So there is the class NN in Torch, and we will use the simple LSTM layer